Alright, so let's look at atomic emission spectroscopy. And this is how we use the atomic emission spectrum of an atom. So I want you to be thinking of color as a quanta of energy. First, you need to know that white light is all colors combined, okay? And the color spectrum itself can be split into three sections. Here's UV, that's over this end. Here's infrared, that's over this end. And this section in the middle, all these other colors, when we join those together, that makes white light, or what we call visible light. So each color itself corresponds to a specific wavelength. Red has a longer wavelength than blue. Now, frequency, which is this here, so E equals HV, frequency, we can work that out, by the way, if we know the wavelength of light. So that's where that's proportional. Now, the wavelength itself is proportional to the energy released. So even though wavelength doesn't fit into this equation, we can use the wavelength to work out the frequency, which is what V is. And as the amount of energy decreases, the wavelength increases. So, using this formula here, once we've worked out the wavelength, we can then work out the frequency, blah, 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 times it, multiply it by Planck's constant, and we find as the energy increases, the wavelength decreases. So, red is less energetic than blue light. And we see this really cool interaction as color. Like, that's where we get color from. But we can also use it to differentiate elements, and that's rad. So the emission spectrum of each element occurs as a result of electrons moving up and down, right, between different electronic levels. Now, what this means is as an electron goes up, it absorbs light, or absorbs energy, and as it goes down, it releases a photon releasing energy. So all level transitions, so from all the different drops, have different energy levels, and this means they move in different, they release different quanta of light, because remember, energy is proportional to the wavelength, and wavelength is the color of light we see. So the emission spectra of each element is different, and it is universal. The emission spectra of a hydrogen element looks the same as any other hydrogen element. Now, notice I didn't say atom, and that's really important. Now, each excited atom emits one wavelength. And what you'll see if you look at sodium is there are sodium, Na, there's 1, 2, 3, 4, 5, 6, 7. Okay, but each atom itself only emits one. But not all of the atoms of sodium will be excited the same way. So, what will happen is they will release different types of energy. But en masse, when you've got more than a few sodium atoms, you get these 7 distinctive bands of light. And there are 7. And they are the same whether it is a group of sodium from one part of the world or a sodium in another part of the world. They will always release the same 7 characteristic bands of light. And that includes sodium that's in stars, by the way. So each element produces different wavelengths. And as they are unique, we can use these to determine what an element is. So where is that useful for us? It's useful in something called AES, or atomic emission spectroscopy. So basically the way it works is, here we have our sample. It is pumped in with fuel, so acetylene, air, fuel, which is what the oxidant is, and the sample goes through and is pumped up into a flame. It's heated up to the point where it emits light. That light is funneled through a slit to give it a beam of light. It then hits this diffraction grating or a prism, either way, and it separates it out. Now this is something emitting pure white light. You can see we've got a full rainbow. That's not exactly what it would happen. It then goes through the monochromator, which will give us individual bands of light, hits a phototube multiplier, and then goes into a computer, which will give us an output that looks like this. So it doesn't actually look like this. This is if we use a spectroscope, but using a spectrometer. Spectrometer meaning meter, measured. Spectroscope meaning it's something we can look at. So here the spectrometer gives us this measurement here, and that is helium. That's what helium looks like. So if we basically can use this to detect really, 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 really small levels of contaminants, such as soil and water, at a crime scene. We can monitor the concentration of many elements in water. So this here is not quantitative. This is quantitative. See, you've got wavelength and then intensity. And that means that's how much of it there is. And you compare it against standards and it will give you certain concentrations in parts per million. It will not give you a direct amount, it will give you concentrations. So we can monitor the concentration of many elements in water, and we can also use it at a crime scene, and we can use it for soil analysis, both agricultural and criminal. Alright, I hope that made a lot of sense. If it didn't, you have any questions, put them in the comments below, and we'll get back to you as soon as we can. Thanks for watching. See you next time. Bye now.